Okay. Well, you're about to sneeze. We might also be interested in the magnetic field created by a circular loop of current, because we talked about the fact that a circular loop of current has a magnetic moment, a magnetic dipole moment, and responds to an external magnetic field. So this is a question of interest for us. And we are interested in, let's restrict our analysis for now to points on the axis of the, I guess the axis of symmetry of the loop. On it, there's more than one. On an axis that passes through the center of the loop perpendicular to the plane of the loop is, I think, what we have to say. It's a little bit wordy, but the picture says everything. We spent a bunch of time, well, not a bunch of time, but we spent a minute talking about sort of enjoying the fact in the previous application that we didn't need to worry about vector components. But here, I think we do. What's different? It's the orientation of the current. The orientation of the current and the point of interest. If we had the circular loop of current and we were on the side of it, then the current would be passing sort of single directionally, I suppose. That's not great, but that's a completely different geometry because of the cross product involved. If we have a current passing perpendicular to the position vector, the point-to-point position vector, from that infinitesimal current to the point at which we're trying to calculate the field, now the cross product kind of rears its ugly head. Imagine, right? You got we're here on the x-axis and there's a ring of current, and the y-axis points up and the z-axis points kind of that way. And we use the right-hand rule for this little piece of current, which goes across the top of the circle that we're looking at. We're facing the circle sort of plane on. So we point our fingers in the direction of the current at that spot, in this case on the y-axis, and then point our fingers so that they point in the position vector from that current element to the point on the symmetry axis. But our thumb now points up at an angle away from, oblique to both the x and y axes, which means we're going to have components. From symmetry, I think we can argue that the perpendicular components, or as drawn, the y component, will have an equal magnitude but oppositely directed y component on the opposite side of the ring of current. And I think everywhere around the ring, just like we had for an electric field, the component in the plane of the loop itself will cancel. And the, I guess, longitudinal component will remain. And that's what we have to sum in order to find the field. To guide our analysis, I'm going to present the solution. But if you're like me, you're too curious for your own good. And I want to make sure. I say that's a weird looking equation. It's interesting that there's x squared plus a squared to 3 halves. That's familiar anymore. I want to prove it. I feel like I can prove it. So I want to take another look at that geometry so that I can reproduce it in a diagram of my own drawing and switch over to the tablet. All right, so we have the y-axis, the x-axis, and the z-axis. We have a circle of current in the YZ plane. All right, and we're interested in this little bit of current here. Sorry, there's some dirt on the stylus here. We've got a current direction this way, and we've got, well, let me label that. We got a current direction this way. We've got the differential length vector dl, which points to in the direction of the current. We've got the point-to-point position vector to point P. And we have the resulting magnetic field according to the cross product, which points this way, perpendicular to the point-to-point position vector. Because the cross product is mutually perpendicular to both dl and r. I'm going to draw that with components. Running out of colors. Draw one in red. And as we consider all the different currents around the ring, those components will cancel. So I actually don't need that. But the components parallel to the x-axis, those will survive. So I'm going to label that bx. And in keeping with the diagram we were just looking at, squiggle that. All right. So let's write down the formula we're going to use. It's the law of biotsavart. Mu 0 I over 4 pi dl cross r hat over r squared. Now, the radius of the loop is a. And we are at a position x along the x-axis, away from the plane of the loop. So the point-to-point distance is, again, yeah, this is going to go, I think this is going to go pretty quick now that we got the hang of it last time. dl cross r hat x squared plus a squared. dl cross r hat. Now, dl, its magnitude is just dl. The magnitude of r hat is 1, and we need the sine of the angle between those two things. But what is the sine of the angle between dl and r? It's tempting to try to label it here, but that isn't the angle between dl and r. That's the angle between r and, I don't know, x. The I hat direction. I think it's 90 degrees. DL is around a circle, right? It's tangential. And it lives in the YZ plane. Now, the point-to-point position vector, R, does have a component in the YZ plane, but that component is radial, right? I'm looking at this. That's the component of vector R that is in the YZ plane. It's radially inward. And if we drew it at a different point, let's say here, it would point radially inward. stand over here at the far end of the x-axis and look this way, what we're seeing is a line from a ring drawn down to the x-axis. And if we just look straight on, that's just going to look like a radius of the circle. The shadow, the projection of that point-to-point position vector is a radius. dl is tangent, and a tangent and a radius are always perpendicular. I'm trying to convince myself that I'm speaking truth. We're talking about a cone, and we are interested not in the angle between the horizontal base and the slant. This is not the angle we're interested in. At this point, the tangent to the circular base, that's dl, points either into the page or out of the page. But this slant, which is our point-to-point position vector, r, lies in the plane of the page. They're perpendicular. Gotta be. So when our formula asks for the sine of the angle between dl and r, it's just 1. Wait, that's the vector field. We need the x component. Now we need the angle that we were looking at before. The angle between pink and green is 90 degrees. So the angle between, if we call this theta, the angle between the x-axis and the red component that I crossed out is 90 minus theta. But pink and green are perpendicular, so the angle between red and green is also theta. So this angle from the magnetic field hypotenuse to the horizontal component, that's the angle that I want to take the cosine of. Isn't the angle that I picked. It's 90 minus that. So I got to call this phi, and then I can label this phi, and then I can ask for the cosine of phi. I want to express it in terms of the geometry of the problem. Cosine is the adjacent, which would be the radius of the loop, and the hypotenuse. And yeah, this is starting to look really familiar, but here the story is even better. We had to do a little bit of pre-work to do this component thing, but check it out. A is the radius of the loop. X is the distance from the YZ plane to the point where we are evaluating the field. Around the loop, if we're integrating DL around the loop, X isn't changing. Nothing is changing. Everything here is constant except, I guess, DL. If we want to integrate, mu I 4 pi x squared plus a squared to the 3 halves a integral dl. The only thing we need to integrate is dl. So we're integrating dl around a circle. That's just the circumference. The circumference with radius a. The 2 cancels the 4, the pi's cancel, and the a's square, and I'm almost positive that is the expression that we left on the slide a minute ago. I gotta be honest, I'm really starting to like this magnetic field calculation. It seems to be easier across the board than the electric field calculation.